Next feature of cryptographic hash functions is hiding the input. To achieve hiding the input, the variable a, which we have seen in the previous slide, will now be merged with another variable z. Z is chosen from probability distribution that has very high min entropy. Min entropy means the distribution is very much spread out so that no value is chosen more than negligible probability. Negligible probability here refers to probability of occurrence of a character. Now imagine as the value as our previous value a combined with z, such that hash of z and a, when it is found, it is not feasible to find the value of a. Now, we just don't want the message to remain hidden forever. We need to reveal the message when we want, like we should be able to use Bitcoin when we need it, and we don't want to hide our Bitcoins forever. So now let's understand how this is achieved through Commitment API with an example. Imagine you have 100 metal coins in a box which is locked with a lock, and you have the key of this lock. So you have this box of coins to show people that you have the box, but only you can open it with the key when you give it to someone. Commitment API also works in a similar way. So here is Commitment API. It would look somewhat like this. With key is a commitment that you are giving, commit message, match is equal to verify, key, message. This statement is used to verify your transaction. Now, to lock the box of coins, that means to encrypt, key is equal to commit message will be used. Then you can publish your that is message. To unlock the key box with the key, that means to unlock the message, you can publish key and message so that anyone can verify and check if the message is valid. In Bitcoin's case, this will look somewhat like this. Commit message is equal to hash of key message key. So you will be hashing the key and the message together, and you will be providing a key. Here, key is a 256-bit value. It's a hash value. Now let's see few more properties of hash functions. Hash functions are one-way functions. This means it's easy for a computer to work forward and find hash code of an input, but it's almost very difficult and unfeasible to work backward and find input if hash code is given. To understand this property, I will show a demo. This is an online hash code generator that I will be using. It's a 256-bit hash code generator which even Bitcoin uses. Suppose I type here hello and I generate hash for this. So this is the hash for word hello, 2CF24DBA etc. It's a 256-bit character, so it's quite long. I just said it's a one-way function. That means from hello, once I generate the hash code, it's very difficult that I can recognize the word hello from this hash code. So hello is not identifiable with this hash code. Not even the H is not visible. You cannot find what was the word from which the hash code is generated. So that proves that it's a one-way function. Now next property is a small change to input changes the hash code dramatically. Let's see this. Suppose I add 1. As you can see, my previous hash code was completely different and this hash code is completely different. What I have done, I just added number 1. Suppose I remove it. See, previous hash code is different, it's completely different. So this and both, if I make any small change like 3, the hash code will change completely. So this is what the second property says. A small change to input changes the hash value dramatically. Hash codes are deterministic, which means same input will always produce the same hash. Now let's see this property in a demo. As I created the hash code with hello, it was always 2CF2 etc. and ending with 24. Now if I change it, hello 2, again hello, again the same hash code will be generated. That means whenever I put the word hello, the same hash code will be generated, which means it is deterministic. So this is what the third property says. Hash codes are deterministic, which means same input will always produce the same hash.